Okay, so now we're going to put into practice all the theory we've been learning in the previous videos. And really, this is a skill that's going to come with actually practicing. So I'm going to give you some general problem-solving techniques for probability questions in general. But really, as I give you each problem, I strongly suggest you put the video on pause and really try it on your own before we go through the solution, because that's the best way to get better at practicing this skill. All right, so here's my overall guidelines for calculating probabilities in the specific case where you have trials of events. So I'm repeatedly throwing die, or I'm drawing cards, or I'm spinning a roulette wheel multiple times. These kind of toy problems that we often give you. The first thing you want to ask yourself is, what event must happen on the first trial? Okay, and sometimes you'll know. So if it's clear based on the problem what must happen on the first trial, then you can likely set this up using the multiplication rule, where you'll say, okay, the first one has to be blank, and then I'll see the second given that the first one was blank. Okay. Now, a lot of times it won't be clear. There's going to be multiple things that could happen on the first trial, and I'm still wanting to calculate a probability. So in that case, if it's like, for example, the first trial could be a king or a queen, you need to list all the distinct ways your event could occur, add up their chances. So in that case, what we're really doing is taking advantage of the inclusion-exclusion principle, where we're saying if I have distinct ways that E could occur, distinct ways, or I'm looking at the distinct ways to get E or F, and if I write them up such that the probability of E and F ends up being 0, so if I really make them distinct, I can just add up the chances of each of the distinct ways. If there's some overlap, you will have to subtract off their probability of their intersection, but in general, you can usually set it up so that you write them up distinctly. All right, and then if that list above, if you start doing that and it looks long and complicated, that's usually a sign that the complement will likely save you some time. And so that's the idea where I'm saying, oh, I want probability of A, but that's really hard. Let me try getting probability of A complement and then doing 1 minus that. So let's put this into practice. In general, though, you'll see how I walk you through going through this right side of the table as you're hitting each problem to decide the best way to start. All right, so first practice question for you. Go ahead, put it on pause. I am drawing a single card at random from a standard 52 card deck. First, I want to know what's the probability that the card is the ace of diamonds. Second, I want to know what's the probability that the card is an ace or a diamond. Okay, go ahead and put it on pause. All right, so my first one is these are equally likely outcomes. My event is that I get the ace of diamonds, so that's only one way I can get that. So I'm going to say that the size, or the number of ways that can be done, is just 1. We can see it right here. My sample space S is all the possible cards, so the number of cards in my sample space is 52. So in this case, just by using equally likely outcomes, I'm getting 1 out of 52. All right, that's a nice warm-up. Okay, now what's the probability that the card is an ace or a diamond? We have a couple ways you can do this. First, I could say ace or diamond, and I could set up that sample space, and I could say how many cards are in that. So if I go look here, I have these 4 aces, and then I have this whole row of diamonds. So altogether, I get 4 plus these additional 12 here, so I get 16. And then my sample space is still the same. So I end up saying that the probability of E here now is 16 out of 52, or 4 out of 13. That's not the only way I could have thought of this. Again, both of these were just using the equally likely outcome viewpoint, which is great when I'm just drawing cards like this. But I'm going to point out the other way I could have thought of this, so I'm going to say option 2, is I could have thought of, okay, well, let's let A be the event that the card is an ace, and let's let D be the event that the card's a diamond. And so I want the probability of A or D, which is the same as A union D. And by using the inclusion-exclusion principle, that has to be equal to this. And now I can go say, okay, well, how many of my cards are aces? Well, that's 4 out of 52. How many are diamonds? That's 13 out of 52. How many are aces and diamonds? That's only 1 out of 52. And that's how I get back to the same answer. So you could have used either viewpoints here when working on this problem. Okay, so let's keep a card analogy, but now I'm going to draw one card. I'm not going to put it back, and then I'm going to draw a second card. So now I want you to calculate what's the chance I get an ace followed by a king, and then what's the chance that one of the cards I draw is a king and the other is an ace. Just go ahead, put it on pause, and give it your best shot. All right, so the first one, I'm going to ask myself, now I do have repeated trials, right? This is like the beginning of the lesson where I said, what if I have repeated trials? And so do I know what has to happen in the first trial for part A? Yes, I have to get an ace based on this. So I'm going to write it specifically like that. I want to know what's the probability that first I get an ace and the second card I get is a king. Because I know what has to happen first, I'm going to write this using the multiplication rule. So this is the probability that first is an ace times the probability the second is a king given the first is an ace. So this is a great use of the multiplication rule. To get an ace first, that's 4 out of 52. And then knowing that I've already taken one card out, now I only have 51 options, but I still have 4 kings out of that. And so this is going to give me 16 out of 52 times 51. Let's actually see roughly what that is just to get a estimate. So that's 4 out of 663, and I'll give you an actual, okay, approximately 0.006. Okay. Now I can look at separately. What's the chance that one of the cards I draw is a king and the other is an ace? So I'm going to show you this 2 ways. The first way is I'm going to go back to thinking of, well, do I know what has to happen first? And the point is no, I have 2 options of what can happen first. I can either do what I had above, the first can be an ace and the second can be a king. Or I could have the first be a king and the second be an ace. Okay, and so really what I'm going to have to do is add those 2 probabilities because either one of those are options. Like I have to account. It's again thinking of the inclusion-exclusion principle on our previous slide here. Yep, where I'm thinking of E as being ace-king, F being king-ace. And so I'm going to add up the probabilities of each of those. And then there's not an intersection because I can't have ace-king and king-ace when I'm just drawing 2 cards. So I don't have to worry about that part. And then to get each individual one, I'm going back up to here because each individual one does have a distinct order. So let's go back. Right. Okay, so this is the same one we did above. This is 16 out of 52 times 51. And so is this one. If I were to do a king first, notice what would happen. I'm still going to get 4 out of 52. And then I'm going to get 4 for my aces out of 51. So now, to add these together, my total, let me give myself a little bit more space, is basically twice. So my probability of 1 king and 1 ace is going to be twice this. So 2 times 16 for 52 times 51. Okay. So that's the first way I can think of this. And again, that's going to end up being now approximately 0.012 because it's twice this. Option 2 is I can use counting principles to think of this because I can really just imagine I'm grabbing 2 cards out of a deck of 52. And so if I want to use counting, this is really where combinatorics is going to come into play, because I'm going to think of E at my event as grabbing an ace. So one ace, one king, unordered. Order doesn't matter. And my sample space is just going to be any 2 cards out of 52. Again, unordered. And so if I do that, I can realize, oh, okay, all the ways I could get 52 or choose 2 cards out of 52 where order doesn't matter, that's 52, choose 2. And all the ways that I could get my numerator here, 1 ace and 1 king unordered, well, I have 4 possible aces and I'm choosing 1, and I have 4 possible kings and I'm choosing 1. And so if I put all of this together, you're going to notice, I'm going to move this up to here just for the space wise. So this is option 2 continued for part B. This means my probability is going to be 4, choose 1 times 4, choose 1 over 52, choose 2. When you do that, we're going to get exactly back to the same thing as this. Okay, that ends up being 16 times 2 over 52 times 51. So I can do either. I like to show you both just so you can think about it either from counting equally likely outcomes or by using our multiplication rule and our inclusion-exclusion principle. Yes, and what I pointed out, so this was still for this same question, is when you're thinking of them in terms of equally likely outcomes, right? I need to be careful. Like, are these equally likely? Yes. I was just grabbing 1 card. I wasn't like weighting them in any way. And then should my objects be ordered or unordered? Well, that really depended on the wording here. All right, next one. You roll a fair 6-sided die 4 times. What's the probability that you roll at least 1 6? All right, so here's one. When I read this, at least 1 6, I'm like, well, I could have gotten 1 6. I could have gotten 2 6s. I could have gotten 3 6s. I could have gotten 4 6s. Already, this is a lot of scenarios to deal with, which is making me think, oh, I bet complement is going to be my friend here. And that is true. It is much easier to calculate the complement. And so what's the probability of getting no 6s in 4 rolls? I'm doing this again in terms of repeated trials. Do I know what has to happen on the first trial? Yes, I can't roll a 6. And so I have a 5-6 chance of that happening. And then I can say, what's the probability of not getting a 6 on the second roll, given that I didn't get a 6 on the first roll? Well, it's still 5-6. The dice doesn't know that there's any what I got before or after. So I can see that I still get 5-6, 5-6, 5-6. I get 5-6 to the 4th. And then I'm going to take 1 minus that, because that was the probability of my complement. So this is a classic example of one where it's much easier to do the complement. Okay, next one. Suppose I have 4 cats and 3 sharks in a bag. They're not real animals, they're stuffed animals. I randomly draw 3. What's the probability of getting 1 cat and 2 sharks? All right, I'm going to show this several ways. The first way is I'm going to think of, because I'm drawing, right, three of these guys. And first I'm going to say, well, do I know what has to happen on the first trial? And the answer is no. I could either get 1 cat or I could get a shark. So to make this work in this process, let's pick one ordering, right? Let's pick one ordering, calculate the probability for one ordering, and then we'll add up all the other ways it could happen. So this is along the lines of order doesn't matter, so I need to start with one ordering and then we'll account for the others. So let's imagine here, if I make this ordered, let's imagine first that I'm going to get the probability that, first I get a cat. Let's make this a little bit easier notation-wise. So I'm going to write it like this. Cat first, shark second, shark third. This is just one possible ordering. Okay, so let's do that one first. And then we'll come over here and say we need to add up all possible orderings. All right, why I like breaking it down this way is because now I can say, okay, I have three trials that I'm doing, but I do know what has to happen in the first trial. I have to get a cat. And so in order to draw a cat, let's see, I have 7 animals total. So that's the size of my sample space. And then the number of ways I could get a cat, the number of items in the event cat is just 4. So that's 4/7. Then I'm multiplying this. Let me write underneath what I'm doing mathematically. That's probability that I get a cat in the first, times the probability I get a shark second, given that I got a cat first, times the probability that I got a shark third, given that I got a cat first and a shark second. That's what I need. So this is the multiplication rule. Again, probability that I get a shark second, given that I got a cat first. Well, now I only have 6 animals to choose from. 3 of those are sharks. Okay, lastly, probability I get a shark again, given that I already have a cat and a shark. Well, now I only have 5 animals to choose from, and I only have 2 sharks left to choose from. All right, so this is the probability of this one specific order. Okay, and now I have to think of, well, that was just one ordering. How many other orderings do I have? Well, let's see, I could have, so I'll say probability of 1 cat and 2 sharks is probability of C1, S2, S3, plus, what's another way it could have happened? I could have gotten a shark first, a cat second, and a shark third. Or I could have gotten a shark first, a shark second, and a cat third. Those are the only 3 ways that I can switch these around. And each of these probabilities are going to end up being, and you can try it out, but they're each going to end up being this 4 times 3 times 2 over 7 times 6 times 5. The orderings move around a little bit, but your product at the end is the same, right? Because if you see what this one is, let's see, I'll just show you. 4/7, 3/6, 2/5. Here, out of sharks, I have 3 out of 7. Out of cats, I have 4 out of 6. And then out of sharks, I'm still going to have 2 out of 5. But you can see they're equivalent. Okay. And same thing with the last one. So I'm going to end up with 3 of these. 3 times this. Oops, let me erase this. And I like viewing it this way because here, this is like the probability of one of the orderings, and then this is how many orderings I get. Okay, that is one way to think of this problem, and it was by starting with an ordered solution, even though we weren't given one in the instructions. But I could have done this from the beginning without thinking of order and just using counting. And so let's think of this way. So what I could say is, let's let S be, I'm picking 3 distinct items out of 7 where order doesn't matter, because I don't have any order specified in this. And my event is that I pick 1 distinct cat, 2 distinct sharks, again, unordered. Okay, then my probability of this whole thing happening is going to be the number of events in E, over the number of events in S, number of outcomes, in E, over the number of outcomes in S. Okay, so how many ways can I pick 3 distinct items out of 7 unordered? That's classic combinations. 7, choose 3. And up here, how many ways can I choose 1 distinct cat? Let's see, I have 4 cats, I'm choosing 1. And then I have 3 sharks total, and I'm choosing 2. So at the end of the day, the probability for our answer, probability of 1 cat, 2 sharks, is exactly this over this, which ends up being 4. Choose 2 over 7, choose 3. And when I simplify, I'm getting 12 over 35, which is exactly the same as what we got on the previous slide. I just hadn't simplified it for us. So if we go back to the previous slide, this exactly simplifies to be 12 over 35 because I get cancellations right there and there. So this is just to point out that you can use different ways of thinking about these problems and we'll arrive at the correct answer either way. All right, here's another one. You have a biased coin. Probability of heads is now Q. You flip the coin 5 times. What's the probability you get the sequence heads, tails, tails, heads, tails? Part B, you flip the coin 5 times. What's the probability you get 2 heads? Okay, so I'm going to point out in this question, I no longer have the ability to calculate probabilities using equally likely outcomes. Instead, I already tell you, I give you the probability of heads. Okay, heads is Q. And so I'm going to have to use some of my rules that we have derived for probabilities. I can't just count events anymore in this. So now I ask myself in part A, I'm flipping the coin 5 times, so I'm repeating some trial 5 times. Do I know what has to happen in the first trial? Yes, I have to get heads. All right, this is telling me this is going to be a good candidate for the multiplication rule. And in fact, that's exactly what it is. So I want, what's the probability I get heads first, tails second, tails third, heads fourth, and tails fifth. And that's exactly, if I spread it out by the multiplication rule, well, probability of heads first is Q. Probability of tails given heads first, well, still 1 minus Q. Probability of tails third given heads and tails, heads first, tails second. This given is really not affecting the probabilities at all here. And we're going to learn in a future lesson that we have a name when that occurs. They're called independent random variables, or independent events in this case. But for now, I still want you thinking of this in terms of the multiplication rule, because sometimes those conditions do affect your probabilities, just like we saw when we were drawing out animals or drawing out cards. Okay, so at the end of the day now, I get Q squared times 1 minus Q cubed for the probability of this specific sequence. Now I want us to think of part B. Okay, I'm flipping the coin 5 times. What's the probability I get 2 heads? Okay, now, is there an order specified in what has to happen first? No, I haven't specified an order. So I can choose an order, like we did up above, like choose an order, calculate the probability, and then figure out how many other orders I would have, right? And add those probabilities together. So I can start with this one. This is one of the possible ways I could have gotten 2 heads. And that probability is Q squared times 1 minus Q cubed. Now I just have to count how many other ways could I have rearranged the sequence and gotten 2 heads. And that's precisely a combination question. It's because it's out of 1, 2, 3, 4, out of 5 slots. I want to choose 2 of them to be heads. So if I choose 2, ends up giving me 10. And these are the 10 possible orderings. Now notice for each of these orderings, the probability for each one of these orderings happening is still this, Q squared times 1 minus Q cubed. So I'm going to add up, right? The probability that I get event 1 plus probability of event 2, well, they all have the same probability in this case. So I'm just taking 10 times that quantity. So this is really analogous to, on our previous example, I'm going to pop back to where you can see this. Here's a good example where I said, yeah, there were 3 different ways we could arrange those, the cats and the sharks, but they all had the same probability. So I have 3 times the probability of one of them. It was the same idea. All right, next question. Population of CU undergrads is 31,000. Suppose you have 100 friends. You walk into a classroom and you see 160 random people. What is the probability that you see at least one friend in the room? And we are going to assume equally likely outcomes in the sense here that each group of K undergrads is equally likely to be in the room. Okay, so here I don't have repeated trials. I am just walking in And I could see one friend, I could see two friends, I could see three friends. So here's an example of, yes, I could add up all of these, or, so I would say doable here, but tedious. This is going to be the way to go, is use the complement rule. And I can just count. So let's let S be my sample space. So the number of ways that I could put together 160 random people out of 31,000, right? Where order doesn't matter. And then my event is greater than or equal to one friend in the room. Okay, so notice what's going to happen now. If we, first let's do this. How many outcomes do I have in this event? Well, I have 31,000 undergrads I'm choosing from, and I want to put 160 of them together where order doesn't matter. So that's 31,000, choose 160. And then let's look at the number of outcomes in e-complement. So the number of ways I could have no friends in the room. Okay, well, again, order is not going to matter. I still need to choose 160 people to be in the room, but I can only choose out of my non-friends. So I'm going to take 31,000 minus my 100 friends up here. Okay, so at the end of the day now, let's put it all together. The probability of E is 1 minus the probability of E complement. So that's this or this. So 1 minus, and now I'm going to have, let's see, 30,900 choose 160 over 31,000 choose 160. And when you do that, you're going to get approximately 0.404. So about 40% chance that you see at least one friend in the room. Pretty good chance for such a huge school. Okay, next one. You take a random survey of CU students and you ask them if they use Facebook and or X. 80% of the students report that they use X, 40% of the students report that they use Facebook, and 3% of the students report they don't use either. Okay, so for this question, we're going to assume that you're choosing a name at random from this sample list. In the future in this class, we'll talk about how we can estimate probabilities for the whole population based on our sample. But for right now, we're just saying we're just going to take a random selection from this sample. And we want to know what's the probability this person uses Facebook or X, what's the probability this person uses Facebook and X, and what's the probability this person does not use Facebook, given that they do use X. Okay, so I would say a starting point here is use the info you have to make a joint probability table, because you are asked to find some joint probabilities, some conditional probabilities, as well as a union. And so having the joint probability table to start is going to be really useful. What I did was just fill in the 3 pieces of info we were given. 80% of the students use X, so I put that right here. 40% use Facebook, so that's here. 3% don't use either, and then based just on these 3 entries, we can get everything else, because we know that this has to add up to 1 right here and here, and I know that this row has to add up to whatever this value is by my law of total probability, and so that's what I'm doing down below is I'm filling in. First I filled in the outer columns, and then use the fact that this had to be 20% to get this one, and then use that to get this one and get this one. So this is where I would start on a problem like this, because I was given information about one of the joint probabilities right there. Okay, now I want the probability that this person uses Facebook or X. I can directly use my inclusion-exclusion formula here. So probability of F plus probability of X minus their joint probability. Probability this person uses Facebook and X. Again, I needed that up above. I got that directly from the joint probability table by using properties of joint probabilities and the laws of total probability. And then lastly, I want a conditional probability, and so that's going to be equal to the joint of not Facebook and X, which I can see is right here. And I want that divided by the probability of x to get what fraction is this of this entire row. And that gives me 57 out of 80. So those are just some practice questions to help you put into or to apply some of the concepts we've learned so far with probability.